Okay, good afternoon, everyone. Let's start the exercise 2. So today, in the following of the lecture by Professor Takeda, which talk about the signal processing, we will have some exercise on signal processing. So is there anyone who did not download, could not download it yet? Nobody. So who could download it? Some people neither download or they are downloading. Okay, everybody has it. So let's move on. If you haven't downloaded, I left the link here, so please use it to download. Okay, the outline. First, I will talk about. Oh, nobody say to me. Okay. Okay, the outline is firstly talk a little bit of Fourier transform, and then we start with the classwork. And in the last part, I will talk about the homework that you have to do based on this. So, okay, Fourier transform, I just go quickly because I don't want to waste your time on that. So as you know, Fourier transform was introduced firstly by him, Fourier, in France. And actually at that time, nobody paid attention to what he did. But eventually it's one of the most important achievements in the mathematical theory. So the concept is very simple. You have he thought that any shape of signal can be represented by combination of several sine wave that you can write a formula with a different frequency, different amplitude, and different phase shift in time. So that was what he thought. And that simple thing becomes Fourier series. So let's say if you have a pulse signal, in the left side it shows, for example, a line plus a sine wave, a line plus 3 sine wave, 4 sine wave. If you add them up together, it gradually changes to be the shape of this pulse signal. So every type of signal can be, so if you add 99 types of these frequencies, you almost get the shape of this pulse signal. So every kind of signal, this is the idea. So you get, let's say, your signal is a combination of these two sine waves, let's say. So this shape is equal to this sine wave and that sine wave. So each of these sine wave has a frequency and has an amplitude. So you can draw it in a frequency domain, say that this signal, this one, has a frequency f with this amplitude and the frequency 3f with this amplitude. So that is called Fourier transform. And so the phase is important, but let's say I will skip about that. So if you add more signal, you get closer and closer and closer and closer, and then if you add all of these sign, you will see that a pulse signal is a summation of, let's say, infinite number of sine wave that the amplitude is reducing, depends on the counting number, and the frequency is also multiplied by the counting number, and this is the spectrum. So that's all for the Fourier transform. So to have, so for those who are not very familiar with this theory, I just wanted to repeat probably the contents that briefly talked by Professor Takeda previously. Okay, from now on, I will move on to the exercise. So firstly, we do classwork and we create M file I'm not sure, last lecture you have been given an M file that was created, but this time you create it by yourself, okay, and do that. So if you could download the material, you can see these PowerPoints. So in a usual our previous experience, some students are fast enough, so they even didn't listen to me. They go on with the text by themselves and finish. Once you finish the classwork and show to one of us that you have done, you can leave the classroom, okay? So if you are confident to do it by yourself, please move on. Don't listen to me, okay? If you have question, please ask after I finish talking or ask other professors, but we should not disturb others who are listening, okay? That's all. So this is the first thing. So you have a command line. Can you open your MATLAB? And in the command line, please type edit. So please open a blank file. Okay, the name is different from top and down. It should be 0. Oh, 1, sorry. Here should be 0. This 0 should be 1. Okay, so signal processing number 1, and in a command line you can create a file with that name. Then you can make an M file like that, and inside the name M file, please type these commands. And I wrote the command meaning, like CLC means clear the command window, clear means clear all variable that is already inside the memory, and close all means close all of the outputs that your previous program had created. So that is like common topping that we normally put on most of the programs. So when you create a program, basically we put that, unless you need to import some other global variable from other outputs to your program. In that case, you should not use clear because it clears the memory. So if you finish this part, I think you already done. So next page, we can create a new file, or okay, you can change the file name. Apparently it should be 0. Sorry. So the next file, you can change the name. You don't care about the name. You can do whatever you like. So please create a M file and create a sine wave. So here, again, we have this topping, clear command. So your previous program, if some windows open after plotting, this plot will be eliminated. And also all variables that are saved in the previous program, like n equal 1000 and r, which is a random number, is also eliminated. Okay? And then this is the sine wave that we want you to create. So the amplitude is 20. Sampling frequency is 1 kilohertz. And the time that we want you to draw this signal is 1 second. And in 1 second, we have 1,000, 1 over 1,000 intervals. So we have nearly 1,000 samples. between 0 to 1. And this is the frequency, and this is your function. So let me show if you finish this 0. So this is the result of the first one. Could you? Okay, if you can create this random white noise you've done. So if you look at the code, so basically is a between it create 1000 data is discrete, is not continuous function. So there are 1000 points here that connected with the line, and the value of these random numbers is created by this function random, and it's range between 0 to 1. So this is correspond the number of random points, and then 1 is the maximum. So if you want to know what this function does, in your command line type help rand, and then you get the explanation about your function. So if you want to know what other types of so just help your function. So it explains to you what kind of variable you can put inside your random function and so on. And also similarly for plot, for title, all this information are there. Okay, so next one is we have a trouble. Okay, the next is the sine wave. So sine wave is also basically the same. If you see the first topping part is the same, clear the command windows, clear all previous variable for the random signal, and close all open figures, like all that random signal should be closed if I run this one. So that is all, and then I define the variables, and then I create a figure, and in this figure I plot function y1 with the versus axis t. And here I add extra command, I call it x label. Of course you can create y label. So x label, it prints time and bracket s next to your x axis only, and on top it says is a sine signal. So in the previous one we had the title, but we didn't have a label for your graph. So when you make a graph in your homework, make sure your graph has a title, has a label for x-axis and y-axis, because who knows what they are unless you say, right? So that's it. So please write this code now. So let's see the result for this one. So if I run sine wave, it should, there is one graph. It will, oh. So this is the first part of this exercise. You should have this kind of signal. Okay. So apparently many of, have you done that? Okay, so let me see my code. So this is the, so what the difference is, I put it 2 seconds. It's the wrong command. For me, it's 2 seconds, so it looks different, right? But in the PowerPoint, I said 1 second. So all of you are correct. If you make it 2 seconds, it will be squeezed. I mean, the frequency doesn't change, but in the display, it looks short, higher frequency. Anyway. So this is the, and then next, let's move on to the next page. We want to convert signal Y1 to the frequency domain. So, and the function black box to convert a signal from time domain to frequency domain is FFT. It stands for Fast Fourier Transform, which is implemented inside MATLAB. And since you convert the signal from time domain to frequency domain, so when you plot a graph in the time domain, it's like this, is a time. But when it's converted to the frequency domain, this axis is not a time, is a frequency. So we define the variable OM, which correspond to the frequency axis. So I set attention here. I wish you think about why this is like this. So this is the answer I give you. So how to, when you convert, but you need to, when you want to draw, you need to do the length of the time that you want to draw and multiply it by sample frequency divided by the length of the time. So there you can get the step from 0 to this variable, to this value. So the result should be like this. If you plot, you add the second part to your program. Yeah, it just continue, yes. Yeah, it's fine. You can make a new M file as you wish, I don't mind. But in the following, we use same variables, so you don't need to clear all variables. So it's just continue on with the same file, if you don't mind. Okay, so have you done that? Not yet. So if you see, I add new function, I call it xlim, means x-axis limit. So it's limit to 0 to f over half of the frequency, sampling frequency. So it shows until 500. So if you notice, this should not be time. Anybody notice? Yeah. So please just don't copy paste what I wrote, okay? Here is not time. I said it's a frequency, right? So you should fix the mistake also. It's part of the class. Okay, I move on to the next one. In this one, we create another signal. We call it Y2, but you have to be careful that this Y2 is different. If you see here, Y2 is the combination of two sine waves. One is sine wave with frequency F1, the other one sine wave with frequency F2, and A1 and A2 amplitude respectively. And the values are here. So you just have to write them here. And then plot Y2, which is the mixture of two sine wave. One of the way that I ask you to do here is to use the MATLAB special functionality, which is based on matrix. So you can, of course, you can say A1 equal to 20, A2 equal to that, and then add them up, same result pop up. But here I want you to use matrix to define two variables at the same time. So if you can do that, it's perfect. If you couldn't do that, it's also okay. But either way, I will show you the way. So first, I would like you to try. So maybe try it for 1 second. I don't know. I try it for 1 minute. It's like this, but it's for 10 seconds, but it's too much. It's not visible. Anybody try to add Y label to the graph? Or play with the X limit or Y limit? Okay, I show you the code if you haven't used matrix, so you can use it. So it's as simple as this. So I say A is equal to this vector, and F is also equal to that, and then I point at A, first element A, parenthesis 1, and F, first element, also F1, and so on. Of course, there are other ways to use that to create this function. Is there anybody try to multiply two matrix and get the same function? I think there is a way to do this, but this is the simplest way. All right, so the second step is to do the Fourier transform of Y2. So we expect you see, because Y2 has two frequencies, so the Fourier transform also should have two impulse shape signal, and this is the Fourier transform. That again, you have to write down this stuff here, and then where is the Fourier transform? Here, sorry. So Y1, no. Y1, Y2, Y3. Yes.
I have an error from Fourier transform one, so I couldn't do
The first one?
Yeah, so I can't do the second one.
Uh-huh.
Could you give me my error?
Okay, this one is the another function I want you try and write the sine wave. And this function difference is that it has only one sine wave, but the amplitude is 20. So if you notice, this is similar to the first component of y2, okay? But the time is shifted. There is a shift in time. So the sine wave is the same sine wave, but it's only shifted with the TD, which is a delay of 8 samples, only 8 samples. So I want you to draw Y3 also. So the third signal that I asked you to create is this one. So you had Y1 and then you had Y2. Y2 has a Y1 plus one extra signal with higher frequency, right? And Y3 is a same Y1, but it has a little bit shift in a signal, a little bit delay. So if you draw, yeah, this is Y3, yes. Yes, yes. Yeah, yes. Same, it's same. Yeah. Actually, in my code, maybe you could have done it or not done it. I'm not sure. So when I plot y2, which is this one, after that I plot the Fourier transform of the same one. So if you see the Fourier transform of y2, you see two components. It mixture of two sine waves, so it should have two signal. And then curve 3 is the one y3 that has a shift in time. But this is a slightly different from what I showed you in the So what I want to ask you do here is create a signal y4 which is y4 equal to y2 So please create this one. Don't look at that. Please create these signals. So what I want to say here, if you see y1, y2, y1 is repeated inside. So if you subtract y2 from y1, you can delete this signal. So this is one of the way to eliminate noise. So if in this signal y1 is a noise, if y1 is a noise, and if we know the noise has a shift of 0 in this signal, so this y1, there is no shift. So if we extract exactly same thing, we can eliminate the noise. But if we don't know the noise has a shift or not, so this is also same. This is also noise. Same noise. It's the same thing. But this is the difference. So one of the way to cancel, I think you hear this thing in the lecture from Professor Takeda, that if you know the noise exactly, so you can cancel the noise by subtracting. Just simple subtraction is the most ideal way to delete the noise. But problem with removing noise is that we don't know exactly what the noise look like. Maybe we can guess what is the amplitude of the noise. Maybe we can guess the frequency. But if we can know exactly what was the delay when it comes, then we can subtract it. So this is some noise cancelling process. So in this case we are successful, but in this case we are not successful. So please plot these two, and after that plus FFT and see what happens. Yes. So the point, I think most of you have recognized that my signal is this one. I want to retrieve this signal from this y2, and unfortunately there is a noise there. And this noise, I want to remove it. If I know the noise exactly, I can remove it. So if this one is minus this one, so only this one left. But this is also the same noise, but only 8 sample out of 1,000 sample it's shifted. Only 8. It's really small, less than 1%, right? So even less than 1% of number of sample each shift, it cannot cancel the noise. That's okay. Let's move on because more than half of the lecture left. Okay. In a file you downloaded, you have a speech file. So please use this function audio read to read the wave file and plot it using this command. So all of these things you can write it in a command line. Of course, you can make an M file for that and write it, but you can do so actually. With the M file is like this, so you can so what we want to do in following, I want you add a sine wave to your audio signal. So we have a sine wave. So in this upper part, you read your audio file and then make a sine wave and then add the sine wave to your audio file. And I want you plot the frequency domain of both the audio signal without and with the sine wave. And then this is some extra thing you can do with that. And play it also. Here also you can play the signal, the audio signal. Sorry, it's too noisy. So it's a audio signal which has a sine wave on top of that. So the annoying part was the sine wave, which is here, this one. So this is the nice one. It's very not nice looking. The nice looking shape is the one which is annoying you. Okay? So please try to use your PC speaker to hear the original signal and the signal with the noise, and also draw the Fourier transform for both of them, the one with the noise and the one without the noise. So we have an audio. Which call it S, and then there is a signal distortion. This stand for signal, and this is stand for distortion is so the distortion is very small, 0.1 amplitude, and frequency is 5 kilohertz sine wave. So it's kind of high pitch noise. You can play with this one, you can change it whatever you like. So you have this one. So for this one, you can create so you have a signal. So please plot it and plot FFT and also play. And also we have S plus D. You also plot it, FFT, and also play. So this is the real signal, and this is the signal, the noise, and then the signal with the noise. And this is the Fourier transform of the signal. Signal has some frequency component around here. Of course, if I remove this one, you will see more. But this is the noise. In the frequency of 5,000, there is a big noise. In the frequency domain, you can see that. So my PC doesn't have the same version as you, so I cannot run low-pass filter. So for me, I will take a rest, and Suzuki Sensei will continue with his PC. So this is the frequency domain of the signal. So you see, most of the frequency of the human speech, even as a woman, is about this area. Of course, woman has more high pitch frequency, so you see this thing. But if you hear a man, if you look at the man frequency domain signal, almost there is nothing here. But when I add the noise to this, there is a big noise here, and the signal is around here. So we want to remove this noise. Okay? So one of the ways to remove it is to know what is the signal exactly and what is the time shift. So if I say, okay, my x is S plus D. So if I know that D, I know exactly D, correct D, so I will say S is equal X minus D. I can extract my signal. But if my signal is T minus 1, let's say, 0.1, something like that, then in that case, if I don't know exact shifting time, T minus, if I don't know this one, I cannot do this one. This will fail. So this is what you did last time. Therefore, it's not easy to remove the noise with simple subtraction. That's why we use filter. So something like low pass filter, high pass filter, band pass filter. So this part, okay, Suzuki Sensei, please do it instead.
Okay, so I'll present you how to build a filter. You can easily build a filter by using a function that is embedded in MATLAB. So first, please select Application tab. Then select click this triangle symbol. Then all filters will be displayed. So from this table, please this one, filter builder. Okay.
I don't have a mic.
Right. So sorry. So what to say?
You don't have to.
No,
Yeah, because you're using your MATLAB, right? Okay. Maybe you should use this thing.
okay. So then this window will be displayed. So please select the top one, low pass. Low pass. So this low pass filter setting will be displayed. So in main tab, please look at this part, frequency specification. From this part, oh sorry. Unit of frequency should be hertz. Then this space will be opened for input sample rate. So please set this part, input here the maximum value of frequency, that is 16,000. Next, please set this one. This means that the band width to be passed by this filter. So please set this one 1900, and the frequency that will be stopped is 2000. Okay. Please select this part. 周波数単位 unit of frequency is hertz. The input sample rate 入力サンプルレートを16000、16,000。そして通過帯域周波数、band width to be passed is 1900、1900。そして、素子帯域周波数、band width to be stopped is 2000、2000。Ah, sorry. Low pass. Yes, low pass filter. Yes. And you can check the form of this filter by click this one. Oh, sorry. Before that, please set apply 適用. Then click this one. This is the shape of the low pass filter created here. So this position means edge boundary of filter that was pointed by the filter builder. So 大体この辺が1900からここは2000です。さっき設定したものです。なので、this part will be passed and this part will be stopped by this filter. So please close this one. And for creating the code of this filter, please select this tab, code 生成, code generation, and select the second one, データをフィルター処理する関数を生成します。And finally, please click this button. Generate MATLAB code. Then this file will be created automatically. So if you use a filter builder, you don't have to write this code by yourself. But if you don't have, your MATLAB don't have such function, please this filter by yourself. And please look at the first line, function y equal do filter parenthesis x. So please just name do file to LPF 1900, low pass filter 1900. And save this code in your computer. For save this file, the shortcut key is Ctrl+S. Then this dialog box will be opened. So the file name is the same to the function of the function LPF 1900 and save. Then this code file is saved in your computer, and you can use this filter. Okay. So I'll explain about this again from start. So yes. First, please apply tab. Then select triangle button and select filter builder. Green icon.
Can you go down for slowly a little bit?
Yes. Sorry. So I'll stop my explanation.
Okay. So he will explain.
From the beginning, yes. Yes, I'll explain slowly. So
anyone couldn't follow, try to listen right now. Okay?
yes. So first, please select Apply tab. Next, please click triangle. Then this table will be displayed. So from this table, please this icon in signal processing and communication, filter builder. Okay. Click this one. Then this window will be opened. So from this one, the low pass filter is the top one. Here, the name is displayed in Japanese. This means low pass filter. And click OK. Then this setting window will be opened. Okay? Okay? So in this wind, please look at this part. 周波数仕様 frequency specification. First, set this one 周波数単位 unit of frequency to be hertz. Then this box will be opened.入力 sample rate or input sample rate. So input here 16,000. This means that the maximum frequency value we set in the previous part. Next, please set input here 1900. This value means the maximum value to be passed by this filter. Then set this part 2000. The bandwidth frequencies more than this value will be stopped by this filter.
I just want to imagine Suzuki said keep this one. So in the last one you had the audio signal. This is the frequency domain that had signal around here, and there was a distortion there, right? If you remember. So this S plus D signal X, this is the spectrum of the Fourier transform of the signal X. So the low pass filter means low frequency passing filter, low pass filter. Okay? So low frequency is passed, high frequency are eliminated. So Suzuki said the maximum sampling is 16,000. For the human speech, 16 kilohertz is the frequency that human ear can hear. So up to this point is enough. And this low pass filter pass every signal up to 1,900, and from the point of 1,900 it start to drop sharply until the minimum point, which is in the 2,000. And then at there it suppressed the signal severely. So this is the gain. So this is like a weight. At this point it multiply this signal by 1, no change, but in this area multiply it by, divide it by 1 over some very big number. Let's say 10,000, 20,000, I don't know exactly. It's decibel. So this is the filter that here is designed. So at the up from 0 to 2,000 kilohertz to 1,900 kilohertz. So this is the blue line. So almost no change. It's little bit fluctuation on top. So almost pass the signal at the point of 1,900, which is this point. Either start sharply to reduce and suppress the signal to minus 60 decibel. So it's a lot of suppression. So if you apply this one to this signal, this distortion will be eliminated. Even we don't know what is the phase or whatever. But what we lose also after 2000, also we lose our signal. So maybe you want to design a filter, come up here. You have more, or here. Or maybe if you are smart enough, you will say, I want a filter that pass everything except this part. Okay? So please think about this thing in your homework, okay? It comes in the homework also. Sorry.
Thank you. You can check the shape of filter by clicking this button. So for creating this, creating the code for this filter, okay. Please select code 生成, code generation. So for creating the code, please click code generation, and from 2 items, select the second one. Okay. And the final step is to select this button. Please click this button for generating MATLAB code of this filter. Then this code file will be created automatically. And in this file, the top line of this file, the function name is doFilter. So you can use this file filter name. If you use this file filter name, the file name also should be also the same name. But here we set this filter name LPF 1900. Please change the top line of this file to LPF 1900. And save this file. For saving this file, the shortcut key is Ctrl+S. Then this window will be opened. And probably the default file name is same as the filter name, LPF 1900, and the extension is .m. So save this file. Then the file name in the tab will be changed to LPF 1900, and the saved file will appear in this window. And the specification of the filter is noted in this file. So if you can use the filter builder, you don't have to write this code by yourself. But if you don't have any such function, please write this file by yourself. Now we can use the filter, low-pass filter function. Okay, any question?
So everybody done.
Now let's go to the next part. So this part, this file is SP2RWDA audio. That was explained by Teherani sensei. So please apply the filter to this signal. So please write this line to your file. S_LPF equal LPF 1900 parenthesis X and semicolon. This line means applying this low-pass filter to the input signal. はい、実行します。
あらゆる物質をすべて自分の方へねじ曲げたのだ。
So it becomes straight, right? It cut the upper frequency, so it does some picture of the human voice. But it removed the distortion, very annoying beep noise, right? So what I wanted to say, best way to cancel noise is to subtract it. But it is impossible if you sub. So therefore, we design filter. To design filter, you have to think what kind of filter is good for removing that kind of noise. So this is one example. So in your homework, you will practice other types. Yeah. Okay. So please, to make you not waiting too long here, I assume that you can do this one later by yourself. So you saw how to make a low pass filter. You can make high pass filter. You can make band pass filter. You can make, this is called notch filter. So it passes everywhere except some parts. They call it notch filter. So if you see, notch filter is a combination of two filters, high pass and low pass. So there is a low pass here, and there is a high pass here. Okay? So if you could not find notch filter in your filter builder, I'm not sure if there is or not. If you could not, you can design two filters and combine the result of two filters and create notch filter. So you can just remove this part and you will hear to the signal much better. There is other filter, we call it comb filter. Comb filter also is a filter look like a comb. So this year I exclude it from the classwork, but it is inside the homework, so please try that also. Okay, this is filtering, and this is the designing low-pass filter that Suzuki Sensei just explained to you. So there is some screenshot, you can follow that. So if you make like that and then press this generate code, you can do that. And apply low-pass filter. And there are some other filter also you can apply, so I just skip for today. Okay. So there is another type of filter, we call it comb filter. So I leave it here, but in your handout today, but you don't need to do it right now. This is the code for the comb filter. So I go to the last part, which is GPS signal. So the GPS data are, I gave you the GPS signal so you can see it. It's something like this. It has a, so do you have something special about this? So it's the GPS, Usui Sensei helped to record some GPS signal. So the GPS device record the day. This is 2014. This is all GPS data. Is it? Or the time is wrong? Okay. It's okay. So anyway, it has a latitude, longitude, and height. So the device, how high from the sea level, and the latitude, longitude in the sphere of the Earth. So from these, you can calculate the location on the planet. So there is a function we call it CSV read. So the Excel file in the format of CSV is readable by MATLAB, and you can read it. So there is a timestamp. So this GPS data that I give you is a little bit formatted. So if you look at this GPS data, it's like this. There is a timestamp, longitude and latitude is like that. So it's different from what I show you as a raw signal. And then I also give you one function in the data I gave you in this link. Is a GPS degree to meter, because this is the Earth, and from the center, the angle to this point, this angle and this angle are given. So I convert this to the meters with this code so you can look at it. And then with that, you can plot it on a 2-dimension. So please look at this code also by yourself. And then, so let's try this part first. So in top, please put the topping of the program you always put. So here is like CLC, clear and close all, and GPS, data, CSV read, and then same stuff. And then unit conversion, and then draw a figure. So this is the new function I put, axis equal. So it will be like a square look of the graph. So if you draw it, you should get such a thing. So please try. So for those who finish this part, draw this one. In the second part, we add noise to the GPS, because in a real life, this GPS is a good GPS, but in a real life, maybe your device has noise, or you get noise from the environment. So we simulate the noise here by adding a normalized noise with the gamma factor. Is a normal noise with the, let's say is gamma, is sigma equal to 5 meter. It's a 5 meter. The noise is in a meter. In a longitude, we add to the longitude and to the x and y direction. So this is the noise. And then you can plot the signal with the noise, which must be like this. So the real signal was less noisy actually, but now it become noisy. So maybe in real life you capture such a signal, you take such a noise, but in order to remove it, here I show you one example. So we apply median filter. You know median filter? Median filter. So in a window of the 11 So what is median filter? So everybody know what is median, right? So I have 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the median here? So 5, 1 both. What is median? Okay.
5.5.
Huh? So what is median? 5? So how many elements we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Manna. So you sort it, you pick the center value. So this is 4, right? So this is median filter, okay? So this is median. There is an average. Average, you sigma all these values, divide by 13. So you can try average filter, change it to average filter also. So by median filter is very good for, median filter is very good to remove the noise. Very good. So, and it doesn't destroy the characteristic feature of signal. It's one of the good noise, but good noise removal filter. But there is a one problem with the median filter is that if you don't know, it's when it can remove noise, it can really remove, but sometimes it cannot do anything. So for this situation, especially for random signal, it's very good. So if you apply this one, you apply the, let me try again. So this is the original signal, this is the noisy signal, and this is the signal after removing noise. So this becomes very close to the original, right? The noisy one has lots of noise, but the noise clearly suppressed, and it becomes very close to the original. This is like median filter. You can apply different type of filter for this. So this is the, if you see the noise, the GPS is in a time domain, right? In a real noisy signal, it's something like this. Professor Takeda in the class explained to you about regression, right? So actually, you can draw a best fit curve of this, right? So this comes in the homework. You can do it in short time. Please take the question pool. We said last week in the program that next week we will distribute a question pool for the examination. So examination is on November 30 at IB. Okay? So here is the question pool printout. Of course, I think Suzuki Sensei also will send you by email. So to make sure you all have it, please take a copy. All right? So you guys, you want to go?
Pieces, for statistics and signal
Cell
processing.
processing, yes. Two of them, yes. Take one per each. So basically, examination is made through this thing, okay? Not 100% equal, maybe 80 to 70 to 100%. You're lucky 100% equal. You're not lucky 70%, 60% similar. Depends on the case. All right, please take it. EPS data, please use the other data I gave you. This is the raw data. So please use them. So apply median filter, smoothing filter, and change the parameters and compare. And then add a noise, and then apply filter. So the sampling data, change the sampling data. It means, for example, you have this sample, suddenly one sample you miss. You have this sample, suddenly one sample you miss. For example, when you walk, maybe you enter to some area, you don't get the signal, like this case. So the person didn't jump from here to here. He walked, but the signal was missing. So by changing the sampling, you make this case more severe, and we want you apply smoothing and those functions on top of that. And also we want to do regression to make the signal like this, make a line of that. And also you can calculate velocity and acceleration from the distance and the time. Okay, more or less is this, and the requirement to submission is by email. And please write the subject of the email and the file name according to this instruction. If you don't follow this instruction and maybe we miss it, then it's your fault. Okay? And deadline is next week. Next week we don't have lecture, right? There's no lecture. Next week no lecture. And the week after is holiday. And then after that we have examination. So any question? And this is the requirement for the homework. So it's very unfair maybe. If you completely answer everything correctly, you don't get full points. You get only 4 points. So all correct is 4 points. But if you answer all correct and do extra impressive discussion, new finding, then we give you outstanding point, which is perfect point, 5 points. All right? To make it competitive. Because mostly get 4 points. Otherwise. Everybody gets 5 points. So we want to make difference between those who can do more. All right? Any question? No? Okay. Thank you.